In this video, we're going to take a slight detour, or maybe I should say a pit stop in our journey through vectors, our little crash course through vectors. And this pit stop will force us to take a look at something that's called a determinant. Now, many of you may have taken a course in linear algebra, and you know a lot more about determinants than we're going to discuss in this video. I am basically just going to introduce a couple simple ideas from linear algebra and then talk about how to find certain determinants. And that's pretty much it. This is not a full look at matrices or determinants. It's just enough to get us what we need to continue along our journey through vectors, right? So enjoy this little pit stop. So I'm going to define what a matrix is. So a matrix, right, is a rectangular array. So is a rectangular array of entries, right? And these entries are arranged in rows and columns, right? And there's several ways that you can represent a matrix. You can have a matrix and you represent it using square brackets. So you have a square brackets and it says it's a rectangular array of entries arranged in rows and columns. So I'm going to write down one such example of a matrix. So you might have something like -2, 4, 1, 0, 3, 3, 8, 11. So this is a matrix that has two rows. So this is row 1 and this is row 2. And then it has 4 columns, right? So maybe I'll do, so this is column 1, that is column 2, this is column 3, and then this is column 4. And we often refer to the dimension of a matrix as the number of rows by the number of columns. So this is an example of a 2 by 4 matrix. So we always put the number of rows first and then the number of columns after. And we don't really multiply them. We keep it like this, right? So we don't say 8, right? We just say it's a 2 by 4 matrix, right? Now, if the matrix has the same number of rows and columns, so if the matrix has the same number of rows and columns, well, we call it a square matrix. Right? So we call it a square matrix. So basically, the fact that a square is a special case of a rectangle. So this example here is not a square matrix because it has 2 rows but 4 columns. Something like this is a square matrix. So 1, 2, -10, 8. This is a 2 by 2 square matrix because it has 2 rows, 2 columns. So 2 by 2 square matrix. And then you can have a 3 by 3 that looks like this. All right, so no particular pattern, just so this one is it should be a 2 by 2 square matrix. This is a 3 by 3 square matrix. Now, for square matrices, there's a very important number that's associated with each of them, meaning given a square matrix, there is a rule, or in fact, there are lots of rules that can be used to compute a certain number, and that number is what we refer to as the determinant of the matrix. So with each square matrix, so every square matrix has one of these numbers. So with each square matrix, we associate a number called the determinant. This is not the discriminant, which is different. The discriminant is, well, the discriminant, you tend to use it a lot when you talk about quadratics or quadratic forms in general. But the determinant, right, is a number that's associated with a square matrix. And so just to kind of give you some notation, in fact, we're going to use one notation to indicate this, and let's say this. So we denote the determinant using what looks like absolute value bars, but not in the context of matrices. So using vertical bars that look like this, right? So what we're going to focus on, and we're only going to do this for 2 by 2 and for 3 by 3 matrices, right? So we're not going to do this in general, and we're not going to get into like the theory of determinants. It's just a matter of how to do this, right? So we're going to define the determinant of a 2 by 2 matrix, and then define the determinant of a 3 by 3 matrix, right? And for the 3 by 3, it's more of a process than, let's say, okay, a formal definition, right? So for a 2 by 2 matrix, so for a 2 by 2 matrix, we find its determinant as follows. So basically, I'm not going to give you like just numbers. I'm going to write down like a generic 2 by 2. So I'm going to put letters there kind of as placeholders. So it would be like this: A, B, C, D. But instead of using brackets, a pair of brackets in this context represents a matrix. But I want to represent a determinant, so that's why I'm going to switch over and write these bars that look like this. So when I see like a rectangular, a square array of entries like this with the vertical bars around it, I interpret this as the determinant of the matrix that's inside. And this is how it's defined for a 2 by 2 matrix. You multiply A and D, you multiply B and C, and then you subtract in that order, right? Now, the entries A and D, they form a diagonal. The entries B and C, they form a diagonal. So for a 2 by 2 determinant, you basically multiply both diagonals, or the entries on both diagonals, and then take the difference, right? So let's just do a quick example of this. So an example of this. So let's say I have the matrix -4, 10, 2, and 11, and I want to compute its determinant. So since it's 2 by 2, basically this is A, this is B, this is C, this is D. So I say that this determinant is equal to -4 times 11 minus 10 times 2. And then obviously I use my order of operations. So I have -44 minus 20, and this determinant comes out to be -64. Now, what I won't get into this, and if you happen to be, or if you've studied linear algebra before, or you're studying it right now, you're going to learn a lot about what this number represents and how it can be used. We are just focused on finding this number, right? So that's what it is for a 2 by 2 determinant. Not a difficult calculation at all. Now, for the 3 by 3, we're going to use a specific process, what's called a cofactor expansion. It sounds fancy, and again, I'm not going to get into what everything is entailed in it, but I'm essentially going to, basically for a 3 by 3 determinant, we're going to break it down into a combination of 3 2 by 2 determinants. So for a 3 by 3 matrix, we find its determinant using the following, what's called cofactor expansion. Right? So again, in fact, let me go ahead up here and just kind of highlight this. So this is a formula to know, because we are going to end up using this several times to compute the determinant of a 3 by 3. Essentially, it is a recursive process, and it can be tedious, but not so much for 2 by 2 and 3 by 3. All right, so let me write down. In fact, I'll do it centered like this. I'm going to write down a generic 3 by 3 matrix. I'm just going to use some letters A, B, C, D, E, F, G, H, I. Awesome. I remembered my alphabet, at least the first 9 letters of my alphabet. My grade school teacher would be proud. All right, so we have our 3 by 3 determinant. And again, these letters, they all represent numbers. They could even represent functions and other expressions, right? But whatever they are, they're arranged in 3 rows, 3 columns. We are going to use what's called the first row cofactor expansion. And it was actually defined by mathematician Simon Laplace. And we're going to use this first row. So I'm going to use the entries in the first row, right? And for each of these entries, I'm going to have to do a special type of calculation, or not calculation, but just kind of a process, and then simplify the results, right? And you'll see what I mean once we get through it. So first, I'm going to write down the letter A. So I'm going to choose the entry that's in the first row, first column. And once I do that, and then eliminate the entire, actually, I think this is what I'm going to do. Bear with me. I am going to, I'm going to copy this because I'm going to use this over and over. So I'm going to put this right next to what we have there, right? And then I'm going to do, let me write down the expression first and then go ahead and do, then say exactly what it represents. So I have my A times that, and then I'm going to do minus B times the same thing. So let me grab this and put it up there, and then plus C. So plus C times the same thing. So there we go. Okay, so so this is what we're going to do now. The thing that we're going to multiply each of these numbers by isn't the entire matrix, but or not the entire determinant, but the determinant of what we call a submatrix. And this is how it works. After I choose the A, I am going to delete the column and the row that has the A in it. And then what's left is going to be a 2 by 2. And that's the determinant that I'm going to use to multiply the A, right? See that? So it's not the full 3 by 3 determinant. So I am trying to compute this 3 by 3 determinant, but I'm actually going to break it down into a combination of several 2 by 2 determinants, right? And then there is this pattern of plus, minus, plus, all right? Now, for the middle term, when I use the entry B, then again, I'm going to have to remove the column and the row that has the entry B in it. And again, I'm going to be left with another 2 by 2 because I have 2 entries left here, 2 entries left here. And then finally, again, when I choose the C, so I have to use all the entries in that first row. And I'm now using the entry C, the entry in the first row, third column. Now, again, I have to delete that third row and that first column. So really, I wanted to include this step so you could see it, but this is what it simplifies to. To evaluate this 3 by 3 determinant, this is the process by which we're going to do it. It's A times the 2 by 2 determinant E, F, H, I, minus B times the 2 by 2 determinant D, F, G, I. So D, F, G, I. And then plus C times the 2 by 2 determinant D, E, G, H, right? Now, this is not a formula to remember. I'm basically just doing it to show you the process of how you go about removing columns and rows and which ones you use and what you multiply by, right? And yes, this is intended to be a negative sign. There's a technical reason why this ends up being negative. It's just a part of the process, right? In linear algebra, or matrix algebra, you would learn where this negative sign comes from, right? Now, we can go ahead and actually simplify this completely and get a really big expression. I'll write down the expression, but this is what it looks like. It's A times, now use the formula that we did earlier. So multiply these, and take a difference. And let me go ahead and put that in for each of the 2 by 2 determinants, right? So this will be EI minus FH, and then minus B times DI minus FG, and then plus C times DH minus EG. Right? And again, these would all be numbers, and then I could finally write down the answer. And that number that we get would be the determinant, or is the determinant of my original matrix. But don't, attempt to kind of memorize this. Let's look at what it is when we do an actual example and focus more on the process. And the other thing I will say, or we'll just do one example. The other thing I'll say, this is not the only way to compute a determinant. There are lots of other ways. In fact, for the 3 by 3s, you have lots of little tricks that you can use if you want to go explore the internet and learn of some other ways to do it. feel free. But this will be the way that I'll be presenting it every time we have to do a 3x3 determinant. So let's say this is what we have. All right, so there's our 3x3 determinant, and we're going to use this first row cofactor expansion. So the first thing I'm going to write down is this entry. So I'm going to take the 5, and when you go to like remove the rows and columns, you can do that mentally. So when I remove the first column and the first row, I'm going to be left with this, which we call a submatrix. So it's like a matrix within a matrix, right? Like that crazy movie with Keanu Reeves. Still don't know what that movie was about. But yeah, so we choose this entry and then remove its column and row and then find the determinant of what's left, and that will multiply the 5. Then I have to do a minus. That's a part of the formula, but the entry in the first row, second column, is also negative. So then this is this -2, and we will fix that when we not fix, but we will simplify that in the next step. And then remove the second column, first row. That leaves the submatrix 1, 9. That's its first row, and then 0, -2. Right? And then to complete the expansion, you have to go across the entire row and then do +3 times. Now remove the third column, again first row, and we're left with 1, 4, 0, -1. All right, so that's the expansion. Now we use the definition for the 2x2 determinant to simplify and complete the calculation of this determinant. Our final answer in this case will be a number. So we'll have 5 times, and then we're going to have 4 times -2, that's -8, and then minus 9 times -1, that's -9. So here we're subtracting -2 times something else, so these two negatives make it a +2 times, and then again use the same 2x2 determinant formula. So 1 times -2, that's -2, minus 9 times 0, that's 0, and then plus 3 times, and then finally 1 times -1, that's -1, minus 4 times 0, that's 0. And then we do our arithmetic nice and carefully. What do we have? So we have 5 times -8 plus 9, that's 1. And then plus 2 times -2, and then plus 3 times -1. So we end up getting 5 minus 4 minus 3. So the determinant of this 3x3 matrix is -2. Right? And again, we're not going to really talk specifically about the significance of this number, but just how to find it, right? So that's just a very, very brief intro into determinants, specifically 2x2 and 3x3 determinants. And now that we've ended this pit stop, let's get back on the road and continue our journey through vectors. See you in the next video.